In lesson 7.5b, we are going to factor polynomials by what we call GCF, which means greatest common factor, in order to prepare them to be solved using the zero product property. So let's go through our vocabulary first. So generally speaking, in the last lesson, we had polynomials that were already factored, and we practiced using the zero product property to solve those, making sure it was equal to 0, and then taking each of the factors and setting it equal to 0 in these little mini equations to find out what possible numbers would make that true. Because the zero product property states that the only way two things multiplied together can give you 0 is if one of those is a 0. Okay, so the reality is, though, a lot of times our polynomials are not given to us already factored. So to solve a polynomial equation using that zero product property, you may need to factor it first yourself. It might not already come factored the way that these examples came in the last lesson. Okay, so we may need to factor the polynomial, or in other words, write it as a product of other polynomials. And then one of the first and most basic ways to do that is to look for what we call a GCF, which means the greatest common factor among all your terms. Okay, so when I say GCF, this is what I'm referring to. What's the greatest common factor among the terms in the polynomial? So this is essentially a monomial that divides evenly into all of your terms. And in fact, it's the greatest monomial that will divide evenly into the terms. So a lot of times you're going to hear me refer to this as kind of the distributive property in reverse. Meaning, you guys are really comfortable at this point using the distributive property. I'll give you just a side note example here. If I had 2x outside of this parentheses, and then perhaps inside I have an x minus 7, right? We know that we can go ahead and multiply that together using the distributive property and making sure that I take this monomial that's on the outside and give it the opportunity to be multiplied by everything in the parentheses. So it would be 2x times x. That would result in a x squared. And then 2x times a negative 7 would result in a negative 14x. Well, what we're doing when we factor the GCF is we're essentially doing that in reverse. We're starting off with this guy right here, right? This polynomial, this whole thing. And we want to be able to identify the fact that 2 goes into both of those, because 2 is divisible by 2 and 14 is divisible by 2, and that there's an x factor that is in both of those. So that would be your GCF here in this particular case. So I would identify the GCF in this problem as saying, okay, well, a 2 goes into both of those terms and 1x goes into both of those terms. I can't do x squared because this second term doesn't have an x squared in it. So I can only, pull as many x's as all of them have. So this guy has 2 x's, this one has only 1, so I can only factor out 1. Okay? And then it's really just, like I said, the distributive property in reverse. We would take that 2x squared minus 14x, we would divide and ask ourselves, okay, well, if we would pull that 2x out to the front, right, and write it outside, what would I be left with? Right, so you divide each one of those, and 2x squared divided by 2x is just x, and negative 14x divided by 2x is a negative 7. And then we would be able to rewrite it like we had the original one. So when we're factoring by the GCF, the main idea is think the reverse of distributive property. Instead of multiplying something into all of the terms, you're looking for something that all of your terms have as a common factor, and you're yanking it out and you're putting it out in front like this. And in the parentheses is just all the other leftover factors. And one really good way to check your answer and know if you did it correctly is that if I distribute that 2x back in, I should still get the original. Okay? This is all going to make more sense when we do several examples. But just so you get that concept of using the opposite or the reverse, of the concept of distribution. Okay? We're going to be factoring a common factor out and putting it out in front of the parentheses. Okay? So check out this example right here. So finding the greatest common factor when we're doing polynomials is we're going to look for the greatest common monomial that goes in the book, right? So let's say that I want to factor out the GCF from 4x to the fourth plus 24x to the third, which is, this guy right here. And so I would treat them each separately and just kind of do one thing at a time. Ask yourself, first of all, what's the biggest common factor between 4 and 24? Okay, so what is the largest number that goes into 4 and 24? So you might start with like, okay, well, 2 goes into both of those, and that is true, but is that the largest, right? So 2 goes into both. I could pull the 2, but that's not our greatest common factor. That's just a common factor. And then I think, oh, wait a minute. 4 goes into both of those. 4 goes into itself, and 4 goes into 24. So the GCF of 4 and 24 is 4. Okay? So I know that those are both divisible by 4, and that is the greatest thing they have in common as far as numbers. Then let's talk about the variables. Okay? The GCF, if you think about this, right? In fact, let's break this out. If I have 4x to the fourth, remember that really means 4 times x times x times x times x. Now we know that 24 can be written as 6 times 4, and then we have x times x times x, because this one's just x to the third. So if we think about what these guys have in common, right, we already established that the 4 was in common, but they apparently also have 3 factors of x, right? That would be our GCF right in there, all those factors that they have in common. So they definitely have a 4 that goes into both. We had already established that. But then we have, as far as the variables, the reality is that the lowest number, that's usually your GCF, right? So even though the top one has 4 x's in it, if the other one doesn't, then that's not a common factor. This last one right here is one they do not have in common. They only have 1, 2, 3 that they both have in common. Okay? So as a way to remember that, and I would write this down, you basically, when it comes to variables, you guys have done GCF with numbers before, but this might be the first time you do it with variables. So when it comes to variables, think of it this way. Whatever your lowest exponent is, that is the GCF. Okay? Is the GCF of your variable. So if I had an x to the fourth and an x to the third, then the most they'll have in common is x to the third. Okay? I can pull 3 x's from both of those terms. I cannot pull 4 x's from both of those terms because the 24x to the third does not have 4 x's to give me. Okay? It only has 3. So 3 is the most that I can ask. Okay? So once you've decided, okay, well, looks to me like the GCF is going to be the 4 and the x to the third, then to rewrite it from this simplified form right here to the factored form, it really is like the reverse of the distributive property. Okay, I would take basically this guy and say, okay, our GCF is 4x to the third. So if I divide each one of those and yank that out and put it in front, what am I left with? Okay, so if I divide the first term by 4x to the third, well, the 4's cancel, and x to the fourth over x to the third is just x. So that's why we have just an x right there. And in the second term, 24 divided by 4 is 6, and x to the third divided by itself cancels, so I'm just left with a 6. And then what I do is just rewrite this the way it would have looked like before that GCF would have been distributed. So I leave the 4x to the third in front of the parentheses, and then inside the parentheses, I write whatever those leftover factors are. Okay? Whatever the extra factors were that they did not have in common. And I'm going to say it one more time. One of the smartest ways to check your work is to, if not on paper, at least mentally, distribute this back in. Because here's the thing. These two things should be equivalent. One is the multiplied standard form version. The other is the factored version. We talked about standard form versus factored last time. Okay? They should be equivalent to each other. So at any point, I should be able to multiply that GCF back in, and it should still equal the original. If not, I did something wrong. But if I do 4x to the third times x, my first term would be 4x to the fourth. And if I did 4x to the third times 6, I would get a 24x to the third. And that matches our original polynomial. So I know that this works. I know that these are equivalent. It's just that one of them is written in standard form, the original, and the new one is in the factored form, the separated out factored form that has that GCF monomial outside and then a parentheses. That is going to allow us to use the zero product property. Okay, so let's just practice it a little bit. First of all, let's just practice doing this factoring by GCF. Let's start with that. Okay, so if I look at this guy, I'm not solving, there's no equal sign. I'm not going to do zero product property. This isn't even equal to anything. Okay, it's just a statement, an expression. But I want to rewrite it from this standard form and change that over to factored form. Okay, so I want to look at these terms. I have 7z to the 7th and plus 2z to the 6th. Let's find out what the GCF is. Well, let's start with our numbers. What is the greatest common factor between 7 and 2? If I think about what goes into 7 and into 2, what is the greatest thing they have in common? Well, turns out, you probably already guessed this, but 7 and 2 are both prime. They don't really have any common factors. The only things that go into 2 are 2 and 1. The only things that go into 7 are 1 and 7. So the GCF, as far as numbers, is just a 1, which is irrelevant. You can either not write it or you can put a 1, but it isn't going to make any difference. Essentially, we basically say there's no common factor between our coefficients. 7 and 2 don't have a common factor. They're both prime. Okay? Now let's talk about the variable, though. Now the variables, I have 7 z factors in that first term. That z to the 7th means I have 7 z's there. And then the second one has 6 z's. Well, remember what we talked about a minute ago. Essentially, the lowest exponent is your GCF. Okay? So both of these have at least 6 z's they can give me. I can pull 6 z's from the first term and 6 z's from the second term. So that's my GCF. My GCF is z to the 6th or 1 z to the 6th, however you want to think about that. But that's going to be our GCF. Okay? So that means that in a moment when we write this in factored form, I'm going to have that outside of the parentheses. It's going to be hanging out sitting there. Okay? Kind of like before it would have been distributed, right? But what I need to know is what would have been in the parentheses here. So then what I do is I divide each term by that GCF to find out what would go in the parentheses. So in the first term, if I have 7z to the 7th, and I divide that by z to the 6th, well, that actually leaves me with a 7. I still have that. And 1z that got left over in that first term. In the second term, the 2 is still going to be there. Okay, 2 divided by 1 is still 2. But the z, I have 6. I'm pulling them all out to the front. I don't have any z's left in that second term. Okay, so it should look like this if I did that correctly. So 2 things to check for. Look in your parentheses and ask yourself, did I really get the greatest common factor, or do those 2 terms still have something in common? Always do that check, because sometimes we miss some of the greatest common factors. We pull something, but it's not the biggest. So look at that 7z plus 2 inside, and just look at it and make sure, do those have anything in common that I might have missed? The answer is no. We did a good job on this one. 7z and 2 don't have anything in common. So we know we got that right. And then the other thing, of course, is what I mentioned. The z to the 6 should still be in front of the parentheses. I haven't changed or made that disappear. I've just rewritten this, separated out. It's as simple as saying, hey, I'm going to rewrite 15 as 3 times 5, right? That's really what we've done, except in polynomial life, right? We have taken something that was already multiplied and cleaned up, and we're separating it out into 2 things that I know are still equal to the original, like 3 times 5. Just because I pulled out a 3 doesn't mean I just dump it and say, oh, now I have 5. No, I still should need the 3 and the 5, because they still need to equal 15, right? 3 times 5 is still equal to 15, but I would just have it written separately like that. Well, that's what we're doing when we're doing this with polynomials. I still need this guy in here, and then this is the other factor, and I know that at any given time, if I were to distribute that back in, it would still be equivalent to the original. So I know I did that right. Okay? That is the factored version of that polynomial. Let's try it again on number 2. So let's start with the GCF of our coefficients. So 24 and 8 is the greatest number that goes into 24 and into 8. And this is one of those, like I said before, that sometimes we don't catch the biggest. Sometimes I have students say, oh, 2 goes into both of those. And they're right, 2 does, but it's not the greatest. And then I'll have kids that'll be like, oh, no, 4 goes into both of those. That's also true, but it's still not the biggest, right? So 8 is the largest common or the greatest common factor because 8 goes into itself completely and into 24. So as far as numbers are concerned, 8 is the GCF among those two. And then when it comes to the variables, the first term has 3 h's, the second one has only 1. So the most that I can divide out is just 1h. So the lowest exponent is your greatest common factor when it comes to the variables. Okay? So 8h is going to be the GCF in this problem. What it means when I rewrite it, that's going to be outside the parentheses. That's our greatest common factor. And then now it's just a matter of finding out, well, what other factors would have been left inside, right? In the parentheses after I divide that out. Well, let's find out. Let's divide each of these by 8h. Okay, so if I divide each term, let's take a look at the first term. 24 divided by 8 would still leave us with a 3. And then h to the third divided by h would still leave me with h to the second. So remember, we subtract those exponents, right? So that would be our first term. The second term, so let's put our plus here, 8h over 8h. 8 over 8 cancels and becomes 1. H over h cancels and becomes 1. Basically, 8h over itself, anything over itself, is 1. Let's talk about that real quick because that is probably one of the most common places of error. A lot of times students see that. They see that 8h is one of your terms and it's your GCF. And they're like, oh, when I pull that out, it's just I'm going to be left with nothing. I just won't bother writing anything. So this is what they do. They're like, oh, I'm pulling the 8h out, so that's all gone. So I'm done. They just close the parentheses and they don't write anything there. And then they get this whole problem wrong. Because what I have in front of me right here is not equivalent to the original. If I multiply this together, I would only get 24h to the third. I wouldn't have that plus h. It wouldn't be equal to the original. You have got to realize that you're dividing 8h divided by itself, and that's equal to 1, and that is just as important to keep right there. Okay? Then this is still equivalent, okay, because if I distributed this back in, I would get the 24h to the third, and then I would do, I also have to do 8h times 1, which will give me a second term of 8h, and now it is equivalent to the original. So if your GCF ends up being the whole term, remember, this doesn't just disappear, this becomes a 1, okay? Anything over itself is 1. So make sure you remember that. That's a common place of mistake when people aren't careful. All right, let's try this very last one. I'm going to go a little bit faster. 15 and 45 are GCF here. Okay, a lot of people might say 5, and they're not wrong, but that's not our greatest. 15 goes into both of those. 15 goes into itself and into 45. So that's going to be our numeric GCF. For our variables, lowest exponent is greatest common factor. So if I only have one f in that second term, then that is the most that I'm actually able to divide. So 15f is going to be our GCF here. And then we'll divide both of those to see what should be left in the parentheses. So in this first term, 15 over 15 is 1. F to the fourth over f is f to the third. So that should be what I have left in that first term. In the second one, negative 45 divided by 15 is minus or negative 3. And then f over f is just 1. So that counts. Okay? So that should be our factored version. And again, you could always check to make sure, do these guys still have anything in common I left behind? And also ask yourself, if I distribute 15f back in, would I get back to the original one that we started with? That's the best way to check to make sure you did this correctly. All right, so now let's marry this or bring it together with what you learned in the previous lesson about using the zero product property. Okay, this is the whole point of learning this skill, is so that we can use a zero product property to solve equations, even if they're not given to us already factored, as we did last time. They were very nice last time. They wrote them already separated out for us, but now we're learning that most of the time we are going to have to do that factoring. Okay, so if you look at number 4, right, you have 6k squared plus k equals 0. Really, you can't solve this the way it's written right now. Okay, I have two different k terms. They have two different degrees, so it's kind of they don't combine. So it's kind of impossible to just isolate k and get it by itself here. Okay. I also know that there's not a addition property of equality or anything like that. It's not like I can just be like, oh, if these two things add together, one of them must be 0. That's not true. Okay, that doesn't work for addition and subtraction. It only works for multiplication. So I want to rewrite this so that it is written as the product of two factors. I want to rewrite it like we just did on the first three examples in this format right here, where it is rewritten as the product of something times something else equals 0. Because then that allows me to use the zero product property. So the way I'm going to do that, one of the most fundamental ways, is that GCF. So let's take a look at the left side. First of all, make sure it's equal to 0, right? So in fact, let's do kind of a little step-by-step guide here on the side. So let's just write it down. If I write it down, you write it down. Remember that. First things first, always make sure it is already set equal to 0. If it isn't, you do that. Okay, make sure you move all your terms to one side. The other side is equal to 0. That, set that up before you begin. Then, once it's set equal to 0, then find the GCF, like we practiced a moment ago. Okay? Once you know what that GCF is, go ahead and factor that GCF. So you can rewrite it. So factor the GCF. So it's written as the product of two things equals 0. Because once it's written as a product of two things equals 0, then we can use or solve using the zero product property. The zero product property. Okay? So then we can solve using the zero product property. That's the name of the game. This is the big idea today. So write that down, have that as a nice little step-by-step guide, and let's put it into action here on the first one. So it's set equal to 0? Yes. So step 1 done. Second of all, let's find the GCF between those two terms. So I've got a 6k squared and plus k. So as far as numbers, I've got a 6 and a 1. They don't have anything in common other than 1, so no numeric GCF. As far as the k's, well, lowest exponent is the greatest common factor. So I have 1k that they can both kind of give up, right? Or, share and pull out. So k here is going to be our GCF. So that means I'm going to divide this guy by k and that one, so I can rewrite this as k times whatever those quotients are. I'm going to pull the k out to the front. That's my GCF. In the parentheses, let's see what's left. 6k squared, if we divide that by k, it's still going to leave me the 6, and it's going to leave me a k. So I had k squared, so if we divide one of them out, we still have a k in it. In the second term, it's plus, and then the second term, it's just k over itself. I had 1k, I'm pulling it, you have to write the 1 there. Have to write the 1 or it's going to be all wrong. So k over k equals 1, so we still have that plus 1. Okay? All right, and then it's equal to 0. As soon as you write this, guys, it becomes like yesterday's lesson. If k times k, 6k plus 1 equals 0, then the only times that is going to be true is if either this factor is equal to 0 or this factor is equal to 0. And then you solve each little mini equation individually to see what your solutions are. Okay? So the first one is already essentially solved for us. K was already by itself. So one solution is when k is 0. When k is 0, this equation is true. So that is one of the solutions. The other solution is when we solve this. So let's move the 1. So that gives me 6k negative 1. And then divide by 6. And that leaves k alone. So my other solution is that k could be a negative 1/6. So I have two solutions, as we've noticed happens a lot in polynomials. One is 0 and the other is negative 1/6. Those are the solutions that make that equation true. You could plug them both in and you'll notice that both of them make this equal to 0 and satisfy the equation. Let's try number 5. On number 5 here, first things first, is it set equal to 0? Check. Second of all, let's find the GCF. What's the greatest number that goes into 35 and 49? So if I think about what numbers go into 35 and 49, think about, multiples and that kind of thing. Hopefully the number 7 jumps out at you. Okay, 7 goes into 35 and into 49, and I'm pretty sure that is the greatest one. And then when it comes to variables, whatever the lowest exponent is, that's my greatest common factor. So n, because the first term only has one n to give me, so that is the most that I can factor out. Okay. So our GCF on this one is going to be 7n. I'm going to write it out in front and then open a parentheses to see what other factors are left when we divide that out. Okay, So to see that, the easiest way is just divide each one of these by 7n to see what's left. So in the first term, if I had 35n, and I divide that by 7n, 35 divided by 7 is 5. And n divided by self is just 1. So I just get 5 there. The second one, we minus, and then 49 divided by 7 is still 7, and n squared divided by n still leaves an n there. Okay, so again, ways to check your answer. Number 1, look inside the parentheses and make sure we didn't leave any common factor that we missed. So make sure that 5 and 7n don't have anything else in common that we should have pulled out with the GCF and maybe we missed. Okay, but I think we're all confident that 5 and 7n don't have anything else in common. So we know we did that right. Second of all, you can always at least mentally distribute that 7n back in and make sure it still equals the original. So if we do 7n times 5, that's 35n. And 7n times negative 7n is a negative 49n squared. So I know all of that is correct, and that is how you check. But now it becomes like yesterday's lesson. I have this rewritten as a product of two things equaling 0, and then I can apply the zero product property. The only way those two things multiply to 0 is when 7n is equal to 0, or when 5 minus 7 is equal to 0. And then we just solve each one of these separately. So in the first one, we'll divide by 7 on both sides. But 0 divided by 7 is still 0. So that's one solution. And in this one, I'll add the 7n, or you could subtract the 5, however you want to do it. Okay, move this guy. Just did that to keep things positive. I'm a positive kind of person. And then to get n by itself, we divide by 7 on both sides. That cancels that. So n would equal that 5 over 7 fraction. Okay? So for this one, these are the solutions that make that polynomial equation true. There it is. Okay. Try number 6, and then you can check it against the answer key on number 6 and see, if you got it right, see if you can find the GCF, factor it, and then use a zero product property. Okay. So I'll let y'all try that one on your own, and then you can check with the key. Let's move on to number 7 and think about, well, how is this one a little bit different? So if you look at number 7, it's not equal to 0. Like, that's always the first thing I keep saying. Make sure it's set equal to 0. This isn't even set equal to 0. So I need to do that work myself. I need to move everything to one side so that it's just equal to 0. So I'm going to start off here by moving that term to the other side. So I'm going to add 72x on both sides. And so these are not like terms, right? One is an x squared and one's a regular x. So I'm just going to leave them next to each other. So now I've got the 6x squared and the 72x that I added. Those guys are now on the left. On the right, I've got nothing left, and it's equal to 0. So if it's not equal to 0, then just move the term to the other side using our inverse operations so that it is equal to 0. Now, it looks just like the previous ones, okay? Once you've set it equal to 0, let's look for the GCF. Okay, so that's step 2. So what is our GCF here between 6 and 72 and x squared and x? So let's start with the 6 and 72. I'm pretty sure 6 actually goes into 72 because I know that 6 times 12 is 72. And so 6 obviously goes into itself and into 72. That's 6 is definitely part of my GCF. And when it comes to variables, lowest exponent is greatest common factor. So an x. That is a GCF. So to rewrite this, I'm going to write that out in front of the parentheses. And then to figure out what is left, let's divide this out and see what other factors were there. So in the first term, I had 6x squared. I'm dividing out a 6x. That's just going to leave me with an x. 6 divided by 6 is 1. X squared divided by x is just x. In the second one, 72 divided by 6 is 12. And x divided by x is just 1. So this really should be what this looks like when we have rewritten it in factored form. I'm going to say it one more time. Ways to check this is look in the parentheses and make sure there's no common factor between x and 12 that you might have left behind. And also, if you distribute the 6x back in, at least in your head or on paper, it should be equivalent to the previous one, the 6x squared plus 72x. Those are the ways you know you did this perfectly. Okay? Great. So now we have this in factored form equal to 0, and it looks just like yesterday's lesson, and now we just set each one of these factors equal to 0 so that we can solve. So on the first one, all we have to do is divide by 6 on both sides to get x alone, but 0 divided by 6 is still 0. On this guy, all we have to do is subtract a 12 on both sides to get x alone, and that means that x is going to be a negative 12. So these are the two solutions to that polynomial. Okay, let's try. I guess we'll jump over here to number 9. We'll try one more. In fact, pause this, really pause it, try it out on your own, and then if you feel good, we'll just finish out with the word problem. Pause it and try 11. Try 9. Okay, so take a look at number 9. If you went through it, you can see the steps and check those. But the solutions are p equals 0 and p equals positive 3. These are the solutions right here. And you can look at my work to see how I got that. If that feels and look good and you're able to get that successfully, then you're right on the right track. And we'll just finish out with the word problem. So a boy kicks a ball in the air. The height, y, in feet above the ground of the ball is modeled by that equation, where x is the time in seconds since the ball was kicked. Find out the root, which remember is just another fancy word for the solutions, the x-intercepts on the graph, the zeros, it's all the same, right? So find the roots of the equation when y equals 0. So that's really at the heart of this, okay? When it's all said and done, we basically want to solve this for when that y is 0. Okay, so we're going to insert a 0 there and, get the ball rolling. Ha, check that out. No pun intended, right? And get going. All right, explain what the roots mean in this situation. So think about this, right? So we've got the ground, we've got a boy kicking a ball here, or a girl, however you want it in. They kick it, right? And then that lands. So they want that equation, right? That little arc that I just made is modeled by that equation right there, where x is time in seconds, and the y-axis, right, is height. We thought about that one. So we basically just want to solve this for when y equals 0. That basically means when those x-intercepts happen, right? We've talked about that. It's where those x-intercepts happen, when the ball is on the ground. And then we're going to explain what that means once we have it. So first of all, we're going to take that equation they gave us. Oh, sorry. Let's start off with negative 16x squared plus 80x, and we're going to set that height or that y value equal to 0, like they asked us, and we'll solve that. So we'll look for a GCF here and factor it out. So I'm thinking 16, I know, goes into itself. I know also it goes into 80, and the lowest exponent is your GCF. So if I have just one x in that second term, that is the most I can factor. So 16x comes out, and when we divide that out, I should let myself a little more room for that, right? So 16x, let's write it just a little bit lower. So when we divide by 16x here and 16x here, that sometimes helps us see. That leaves me with just a negative 1, and then an x. Okay, so negative 16 divided by 16 is negative 1, and x squared divided by x is just x. And then in the second term here, 80 divided by 16 is 5, and x over x cancels, or becomes a 1. So that is the factored version there of the equation, and then I can use the zero product property to find out what those roots are. So 16x equals 0 will be one of our roots, and negative x plus 5 is going to be one of our roots. So here we'll just divide by 16 on both sides. X equals 0 is one option. Here I'm going to add this x on both sides, and I'm at that 5 is equal to x is the other option. So those are the two solutions. And when I think about what they mean, so first of all, let's just write our roots. So our roots are these two right here. Those are the roots. But let's talk about, explain what the roots mean. Well, remember, we said the height, y, the y value became 0. That means a height of 0. It basically means we're on the ground. So that means that this ball was on the ground at 0 seconds, which makes sense because they probably kicked it from the ground. And then it went up into the air, choo-choo. And then this other one, the 5, must have been when it came back down onto the ground. Okay, so if I make an explanation here, basically these roots, write this down. So these roots, or in other words, the solutions, okay, they mean the ball was in the air for a total of 5 seconds. 6 seconds before hitting the ground. It means that the ball was in the ground on the air for 5 seconds. So right at time 0, at 0 seconds, it's on the floor or on the ground. Boom, we kick it. It goes up, 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 and then it goes back to a height of 0, back on the ground at 5 seconds after that.